All right. Thank you guys all for coming. Today we have a very special guest lectures. Our babbies have been working really hard for these. They've been staying up late nights, blood, sweat, and tears, all for you guys for this lecture today. Just some quick announcements beforehand. We're gonna have a guest lecture from Coinbase. This is really cool. Actually, the person who created this course and created the decal is gonna be coming back. He currently works as the head of security. So head of security at Coinbase, and we really hope you guys show up to this. I think this will be a really exciting guest lecture. And for those who showed up last week, thank you guys so much for showing up. I heard it went really well. There's also no more quizzes, so just enjoy the show for this one. And the final paper is going to be due Monday, 5/1 at 11:59 p.m. And it's going to be 600 to 800 words. And you can write about anything. Please don't use ChatGPT. We will check, but whatever your heart desires, you can write about. All right, our first bag lecture is going to be Will. And Will wanted to play a quick song just to get him fired up.
That's the Will. The intro.
Right. Thank you.
You guys normally clip this?
Yeah.
Oh, I might just hold it.
Whatever's more natural.
Okay. Let's see. I can try to clip this. It is. Test. Okay, this is good enough. Is it? All right. You guys want to wait for the chorus? No. Okay. Never mind. Oh, it started again. Okay. Oh shit. All right. Let's. All right. Moving on. I don't know, dude. What is going on?
Wait, what? Oh, no, it's fine. That's just like.
Oh, okay. Very cool. All right, guys. Well, yeah, I don't know how to deal with this mic, but I think I'll just hold it. I don't know.
Okay.
Yeah, it's on. Okay. Yeah. All right. Yeah. So, hey, everyone. My name is Will. I'm a second year studying CS business. I joined BAB this past semester. And today I'll be talking to you guys about Compound. So I know you guys have previously covered a little bit about DeFi, just like as a whole. So for this lecture, I'm going to be doing more of a deep dive into a specific topic or protocol. So just an overview of what I'll be covering in this lecture. I'll start off by talking a little bit about blockchain lending in general. Then I'll be talking a little bit more about Compound specifically and how Compound works. And then I'll go into more about how Compound is governed, as well as just a quick summary at the end of the key takeaways. Now, before we get started, here are some of the key finance terms that I may be using throughout this lecture to explain the concepts. So some of these terms maybe you've seen before, some of these maybe not. But just for reference, these are a few of the key definitions. And if at any point you guys want to refer back to these definitions with a little bit more detail, you can scan this QR code or go to this link listed above, and you'll be able to refer back to those definitions. So I'll just leave this up for a quick moment if anyone wants to scan. Right. Okay, so now let's talk a little bit about blockchain lending. So first of all, what is lending in the real world? As I'm sure most of you guys are probably familiar with, lending is essentially a practice where you allow a person or organization to borrow something, usually money, with the expectation that they'll pay it back later. So common examples of this are like your credit card, a student loan, or maybe a mortgage. And typically in the real world, these are facilitated by banks, which lend out their depositors' funds. Now, this is a little bit different on the blockchain, where you still have the process of like depositing and lending out cryptocurrencies. But in many cases on the blockchain, you actually don't need any central authority like a bank. Instead, you often have smart contracts, which can programmatically handle the lending. And so compared to banks with lending on blockchain, you can often get lower borrowing costs, you can earn higher interest as a lender, and you get greater transparency into how the whole process works. Now, some of the purposes of why someone might want to lend on the blockchain, for lenders, the clear draw is you get a lot of interest. So if you just have a lot of crypto lying around, not really do anything, you might as well let it like earn interest and compound over time. And with crypto lending, depending on what asset you have, you can actually earn much more interest than you would in a bank account. So for some assets might go as high as like 15, 20%. Whereas the average bank account, I actually just checked this morning, it's like under 1%. And has anyone heard of the new Apple announcement with like the 4% savings account? Yeah, I felt inspired this morning. I decided to open one. So you can even get even higher interest on crypto if you guys want. And yeah, beyond that, just beyond the higher interest, you can also just have more transparency into how the whole lending process works. So for example, here, this is a screenshot from the open source code of Compound. So the whole community can see like exactly how the process works and how like whether there's potentially any vulnerabilities that need to be fixed. And as a result, you just get more transparency versus like a bank where you kind of just deposit your funds and it's a black box as to like what they do with your actual money. Now, on the other side of the equation for borrowers, the draw of crypto lending is basically just accessible capital for purposes that are mainly financial at the moment, but in the future, potentially more like business oriented. So one of the key applications of lending today is amplifying your potential returns or losses through a strategy called leverage. And basically this means using borrowed money to increase your own returns. So like, let's say if you want to invest in a stock and you only have so much money, but like you think the stock is going to go up a lot, you could borrow money to buy even more of that stock and then earn more potential returns. This could also be losses, so tread carefully. In the future, lending might also be used for investing in business growth when crypto is used for more like everyday commerce. And for borrowers, you can often get lower interest rates than your traditional loans at a bank. And it's also often more accessible. So especially in areas where like financial institutions aren't as well established, as long as you have an internet connection, you can get access to crypto lending. Now, here's just an overview of the blockchain lending ecosystem. So they're roughly split into centralized and decentralized platforms. With centralized platforms, you kind of have to, they function a little bit more similarly to a bank, and you have to kind of trust that they won't like misuse your funds. And they facilitate both fiat and crypto lending. So some examples are like Binance, Unchained Capital, uHodler. Whereas decentralized platforms, they facilitate crypto lending through just automated smart contracts, and you don't have to trust that they won't like do anything fishy with your funds. And some examples are Aave, Alchemix, and Compound. Now, obviously, there are definitely some risks associated with blockchain lending. So the main thing with blockchain also as a whole is just volatility. So a lot of price volatility can actually end up in you losing money if you lend out your crypto. So for example, if you lend out like 1 Bitcoin and the borrower then has to like repay you 1 Bitcoin with a little bit of interest, regardless of what the like dollar value of Bitcoin is. So for example, if you lent it out when Bitcoin was like $60,000 and then the borrower repays it when Bitcoin is like $10,000, you would have basically just lost $50,000 when you could have instead just like sold your Bitcoin and kept your value. Another issue is liquidation. Because of the volatility, there's a mechanism in place called liquidation where the lender can potentially sell your collateral if it falls below a certain value threshold. And if that happens, you end up usually taking a loss. And so this is an example on the side here where like because the collateral value can be very volatile, if it falls below some certain value, it will get sold for a loss, and you as a borrower would end up taking a loss. And then beyond that, there's also just risks relating to the lending platform itself. So this is often an issue with centralized platforms where you have to trust that they won't like misuse your funds. And a lot of these lending protocols could face like security, regulatory, or other financial risks that could end up resulting in you not being able to get your funds out. And you've definitely seen some examples in the past year with protocols like Celsius, Voyager Digital, and BlockFi. All right, so before we dive into Compound, any questions on like blockchain lending in general and the different types of platforms out there? Yep.
It looks like lenders get a higher interest compared to traditional banks, but at the same time, borrowers also get a lower interest. So how does that work exactly?
Right, so a lot of that is because there's no middleman involved. And so like traditionally in a bank, the bank would like keep the spread between like what they lend out to borrowers and what they pay their depositors. And the banks have like a lot of costs to deal with, like having their physical facilities, paying their employees. Whereas on a blockchain, because there's no middleman, a lot of this can just be automated and there's no like middleman that has to take some of the costs. And so as a result, there's like less spread between the two interest rates and like you can offer better terms to both. Yep. All right, any other questions? Okay. So let's move a little bit more into Compound specifically. So what is Compound? Compound is one of the leading decentralized lending platforms. It's built primarily on Ethereum and Polygon, and it enables borrowing and lending through smart contracts without a central authority. As of early April 2023, there were $2.4 billion in collateral assets and around 734 million in borrowed assets. And if you want, you can check it out at compound.finance. So a little bit of history about Compound as a company. So Compound Labs was founded in 2017 by Robert Leshner and Jeffrey Hayes. They saw a lot of gaps in like the crypto borrowing options, as well as just wanting to build a more complete financial system on the blockchain. So in 2018, they launched Compound V1, which was the first iteration. This was one of the first like major lending platforms that eliminated many of the frictions of peer-to-peer lending. Then in 2019, they launched Compound V2, which introduced C tokens to represent lender balances and made governance more decentralized. I'll talk more about the details of this later on. And then in 2022, they also launched Compound V3, which enhanced risk management practices by basically restricting like which tokens you can borrow. So this is an example of how you would use Compound V2. This is what the interface looks like. And essentially first you would connect some Ethereum wallet like MetaMask, Coinbase wallet. You would supply your collateral tokens. And if you just want to lend out your tokens and earn interest, you can basically just supply it, let it sit, earn interest, and take it out whenever you want. Otherwise, if you also want to borrow, you would have to put down collateral in the same way, and then like borrow some tokens against your collateral if you want. And you can see here on Compound V2, there's a lot of different tokens that you can supply, and there's a lot of different tokens that you can borrow as well. All right, so that's a quick overview of Compound. Any questions before we dive into how it works? All right. All right, so let's dive a little bit more into how Compound works. So let's start off from the lender perspective. So for a lender, let's say you want to deposit your money into Compound and earn some interest on your crypto. Essentially, what Compound does is it aggregates the supplied assets of all its users so that it can be used as a big liquidity pool for borrowing. And so when a user deposits the tokens, they receive what's called C tokens in return that basically act as a balance, saying that, okay, Compound acknowledges that you deposited this amount of tokens with us, and if you want to withdraw it, you can redeem it at some exchange rate. Now, C tokens can also be redeemed at any time, which gives you a lot of flexibility in terms of when you want to take your money out or put it back in. So you can kind of see a diagram down below here, where if Alice wants to deposit her ETH into an ETH borrowing pool, imagine there would be like a lot of other potential lenders as well. They would all their funds would get deposited into this borrowing pool that gets lent out to however many borrowers there are out there. And in return for depositing their ETH, they would get the CETH token in exchange, which Compound uses to say like, okay, we acknowledge that this is like how much ETH you deposited with us. So let's walk through an example of how this might work in terms of earning interest. So let's say here first that Alice deposits $100 worth of ETH into the ETH borrowing pool, and the current market interest rate is 5%. Now let's say that Compound gives Alice an equivalent amount of ETH, of CETH, based on what the current exchange rate is. So let's say for simplicity that it's a 1-to-1 exchange rate of like $1 of ETH is equal to 1 CETH. Now, let's say that 1 year later, Alice wants to redeem her original ETH with interest. And basically how this would work is the exchange rate between CETH and ETH would have gone up in order to give her more interest. So even though she still has the same 100 CETH, basically during that 1 year time span, the exchange rate would have gone up so that by the time she redeems those tokens, she can actually get $105 worth of ETH back. And I'll talk a little bit about like the math behind this. You don't need to like know too much about this, but basically the exchange rate is determined by these 4 variables, like underlying balance, total borrow balance and reserves, and the C token supply. So underlying balance here is like the total amount of cash that's available in the lending pool. The total borrow balance is the amount that's like currently being lent out, and reserves don't really have to worry about too much, but it's like a small cut of interest that Compound keeps for itself. And C token supply is just like set by the protocol. So we can walk through an example scenario where let's say that currently the exchange rate is 1 CETH. You see if I right here?
Yeah.
Okay, I think this should be good. Okay, yeah, so let's say that right now the exchange rate okay, I don't know if it's a super visible, but I'll try my best. This first exchange rate now is 1 CETH is equal to 0.02 CE or 0.02 E, and this is determined by some underlying balance, which we don't really care about too much. So let's say it's just U, and then we have the total borrow balance. Let's say that it's $100. And then we don't care about reserves too much, so I'll just note that as R. And then let's say that we have 10,000 C tokens supplied. All right, so now let's say that after 1 year, as interest accrues, the total borrow balance increases to $105. So now the exchange rate would be equal to, so ER2 would be equal to U plus 105 R over 10,000. And then you can kind of distribute this out a bit to where this would basically be equal to 0.02, which is the original exchange rate, plus 5 over 10,000. And this would end up being 0.0205 ETH. And so basically what this math is saying is that as the exchange rate or as the borrow balance goes up because interest is being accrued, each CETH token that a lender holds will be worth more and more ETH. So basically, because this exchange rate goes up, by the time you want to redeem your actual underlying ETH afterwards, you're able to get more with interest. Okay, so before I move to kind of the borrower side, does anyone have any questions about how this works, how like the exchange rate math works, if you're curious? All right, if not, we can move on to the borrower side. So in terms of borrowing assets from Compound, borrowers essentially have to first supply another token as collateral. And most crypto lending platforms do this where you have to collateralize because there's not really too much of a concept of like credit scoring or evaluating someone's creditworthiness. And so the only way to really make sure that like lenders can make sure they get their money back is through collateral. And in crypto borrowing, oftentimes borrowing is over collateralized. And this means that you have to put down more in collateral than you can borrow out. So there's a collateral factor, which is like a borrowable portion of your collateral value. And this depends on the volatility of your collateral asset. So for example, like if you deposit a stable coin like USDC, which is fairly stable and like reliable, you would be able to borrow a higher portion of that in like some other token compared to if you deposited a more volatile asset like Dogecoin, for example. So you can kind of see an example of this of like, let's say you had $100 worth of Bitcoin and you put it down as collateral. If there's like a 50% collateral factor, that means you would only be able to borrow up to $50 worth of ETH. So you can't borrow like the full $100 out. And if your collateral value actually falls below a certain threshold, then like mentioned earlier, your collateral would get liquidated, which means that basically, let's say if you got liquidated here, then your $100 worth of Bitcoin would get sold off by Compound in order to help like recoup any potential losses. And then you would end up just keeping the $50 worth of ETH. Now, a question some of you might have is like, why would you want to borrow less than the collateral amount that you already have? So one of the key reasons here is diversification, and it's that you can get exposure to a wider variety of assets at the same time. So let's say that like you like both Bitcoin and ETH, but you don't want to have to like sell some of your Bitcoin in order to buy that, or like you don't want to just like you only have so much Bitcoin, you don't want to have to like reallocate that portfolio. What you can do instead is like you can get Bitcoin and ETH at the same time by borrowing. Like you put down your Bitcoin as collateral, so it's still your property, and then you can borrow out ETH, so you get exposure to that and can earn some potential returns. Another use is leverage. So you can amplify your potential returns using other people's money. You kind of see an example of this where like, let's say you really like ETH, but you only have $100 worth of it. What you could do to increase your exposure through leverage is you put down your $100 of ETH as collateral, you use it to borrow out $50 worth of another token, let's say USDC. You can then take that USDC and exchange it on like an exchange to get more ETH. So now your exposure would be $150 worth of ETH. Another application is shorting. I don't want to go too deep into this, but basically this is a way for you to profit from an asset that declines in value. And the way that shorting works is essentially you would borrow out some token that you want to short, you sell it immediately. So that let's say it's like at a higher price right now. And then in the future, you hope that like the price goes down and then you can buy it back at a lower price. And then the difference between the price that you sold it at and you bought it back at is the amount of profit that you get to keep. And then finally, liquidity might be another reason why someone might want to borrow. This is just for like paying down your obligations without having to sell the assets that you already own. And you can kind of think of it in the real world, like if you have a really expensive house, but you don't have enough cash to like pay your bills, then instead of selling your house to get the cash, you could just like borrow against your house in order to like just cover your obligations. Now, in terms of the interest rate, this is a key factor that Compound wants to account for to make sure that like they're creating an efficient money market. Basically, what they do is they want to encapsulate the supply and demand for funds with a metric called the utilization ratio. And this is calculated as the total balance of borrowed assets over the total balance of like available cash plus borrowed assets. And basically this just means you can kind of think of this as like when utilization is low, like towards zero, that means that there's like few borrowed assets, but a lot of like cash essentially. And that just means there's low demand for borrowing, but like high supply of funds. Whereas on the other end of the spectrum at like 100% utilization, that would mean that everyone like wants to borrow assets. There's really high demand for that, but there's not much supply for funds to be borrowed. And so with that one metric of utilization, you can kind of capture both supply and demand. And the interest rate is then calculated as a function of this utilization. It's usually calculated as like a linear function, and like the specific parameters can be set through like governance. And as funds become scarce, the interest rate increases like more drastically. So you can kind of see on this graph here, there's like a kink at a higher utilization. And that's basically just trying to prevent like a liquidity crunch where like if there's not much money that's like still left in the pool, then they really want to make sure that like there's still going to be more people who want to put their money in, or like make sure that like people repay their loans back sooner so that you can maintain like a more sustainable equilibrium of like just having more cash on hand. All right, and then a little bit more about Compound V2 versus V3, which I touched on a bit in the history. So in V2, as you saw earlier, there were a lot of different assets that you could borrow or supply. And basically, that's like one of the key things that Compound V3 wanted to change. So V2, it enables this, and your collateral can then be like, can earn interest as it gets lent out. So because you can have this like multi-asset supply and borrow, if you put down some amount of collateral, it's like in a different token, they could then like take it out and lend it to someone else. And so you can earn interest on that. And it gives you more flexibility with like these different assets. but it's also risky because one bad asset in the pool could spread risks to like other asset pools that aren't like directly related. And so V3 wanted to fix this by restricting the borrowing and supplying to a single base asset per deployment. So there's fewer assets that you're allowed to put down as collateral. And currently there's only deployments that allow USDC and ETH to be borrowed. And then in this case, your collateral is never able to be lent out because there's only one borrowable asset. And this also just helps to reduce the systemic risks to the protocol as a whole. And you can kind of see these differences in the interfaces, whereas V2 lets you have like a lot of different assets you can supply or borrow. V3, like this is just one deployment. It's for USDC on Ethereum. So in this case, there's only 5 tokens that you can supply as collateral, and you can only borrow USDC on this deployment. And this just helps to reduce like some risks. But currently, most of the value on Compound is still locked into V2. So basically, that was the whole overview of how Compound works. I know it might have been a lot. So does anyone have questions about how any of this works? Whether it's like C tokens, borrowing over collateralized, anything like that? Yep.
Do you pay taxes?
So I'm honestly not too sure about this, but I believe like as long as you, sorry, let me think. So I know that like in some regards, like lending can help you kind of delay your capital gains taxes at some point, because then you don't have to sell like back into like the fiat world. So from my understanding, I think it might be like once you go back to the fiat world and kind of like cash it in, then you might have to pay taxes. But honestly, I'm not super sure. Yeah. All right. Any other questions? All right. If not, I'll talk a little bit more about Compounds, like code implementation and like architecture. So this is a little bit more technical. It's not like super conceptually relevant, but for those who are curious. So one of the things that Compound does to track the historical interest rates is it uses an interest rate index, and it's kind of treated as like a global state, and it updates every time funds flow in or out of the pool. And it's like kind of measured by this formula, which essentially every new index is the previous index compounded at like some interest rate. And you can kind of see like what the variables are here. And basically this is like just to keep track of the history of the interest rate. And it's a little different than like the actual rate that's quoted, because it's just for like record keeping, like historical data tracking purposes. And then this functions sort of similarly with the total amount that's being borrowed, where like when the interest rate is updated, the total amount that's borrowed out is also updated to reflect the interest that would have accrued during that time period. So this functions exactly to like compound interest. Basically, like the total balance, the new total balance is equal to the old total balance times like some interest rate that you compound it by. And in terms of the actual borrowing and liquidation mechanisms, so there's functions called like borrow that basically like let you borrow. You can repay it at any time with the repay borrow function. And in terms of like liquidation, so we established earlier that this occurs when like the user's collateral falls below some value. So this can actually be from like, you can also get liquidated if the assets that you borrowed appreciate in value and then get like too close to the value of your collateral. So it can go both ways. And basically the way that this works is there's a reward that's given out to the first community member who like buys your liquidated collateral at like a discount. So they would get your collateral at a discount and basically help repay whatever amount that was lent out. And they also get like a small reward on top of that. And a price oracle, which is basically like a third party, like outside data source, is what they use in order to track these exchange rates and determine when something might be liquidated. All right, so that was just a quick overview of like some of the actual code implementations. If anyone's curious, have any further questions about that? Yep.
So the first one, right under this.
Yeah.
It says can be complied with depreciated or borrowed assets that can.
Right.
So why do you get liquidated if the borrowed assets are pension?
Yeah, so the reason that can happen as well is like, basically they always want to maintain that there's enough value that's like backing up your borrowing. And so basically if there's not enough backing up your borrowing because your collateral falls, then like that's worth liquidating. But then also if your borrowed assets increase in value, then and it's like getting too close to your collateral value, then it's like, okay, there's not as much margin for error of like, if it maybe it could like keep going up, or it could like drop sharply. And they always want to maintain like a cushion to make sure that like lenders can get paid back no matter what, because with the collateral. And so if the borrowed balance gets too high, that also becomes a risk where like you might end up having the case where the borrowed balance like exceeds the collateral value, and you don't want that. So that's a reason where you could also get liquidated.
Wouldn't that make it more likely for you to be able to repay your loan if your borrowed asset is high?
Yeah, but I think generally like these crypto lending platforms just don't want to really take that risk, because maybe it's like it just shot up really high like on like some news that, and it's not a sustainable rise. And so they just don't want to take that risk. They want to make sure that lenders can definitely like get their money back. Yep.
How do they decide that crypto reward is how much of a discount is for the liquidated value?
Yeah, so honestly, I don't know too much about the specifics of the implementation, but basically this is just an incentive to make sure that like if a borrower's collateral needs to be liquidated, then there's like an incentive for people to actually liquidate it. And so people would like just basically the reward is only given to the first person, and this, I guess it would have to be substantial enough that like they would want to make sure that like they liquidate first so that they can like get some profit out of it. But I don't know too much of the specifics. Yep. Any further questions? All right. Now we can move on a little bit more into governance. So I touched on this a little bit earlier, but basically governance is a way for the community as a whole to make edits to the Compound platform. So essentially Compound is composed of a lot of different smart contracts that are like deployed on publicly on a blockchain like Ethereum. And these smart contracts can be updated or upgraded. And basically the way that this would work is through an admin smart contract called Governor Bravo, which has like basically admin authority over the core components of Compound. And through Governor Bravo, the community can essentially update different aspects of the Compound smart contract. So things like the interest rate model, let's say you wanted to change the parameters of like the linear function of like utilization to determine the interest rate. If you want to change that, you would have to go through Governor Bravo. Also, if you want to change the supported assets, so like let's say you want to add a new asset that you can use as collateral on one of the deployments, you would also have to go through Governor Bravo to do that. Oh, and the way that this works is through what's called proposals. And basically these proposals decide what updates that Governor Bravo is going to make to Compound. So you can kind of see an example here where so this is on the Compound governance website. You can see some of the recent proposals that have been made. One's like for Compound V2 to V3 migration. Basically, these proposals get proposed to the community through like the governance platform. And these proposals are then voted on by the holders of the Comp governance token. And basically, in order for a proposal to actually go through and get executed, it has to basically like win a vote. And basically, the more comp tokens that someone has, the more votes that they have in this process. And your comp tokens can also be like bought and borrowed or used as collateral. And yeah, essentially, it's just a way to make the governance more decentralized and like having the community decide on these big decisions, rather than having like Compound Labs as a company having central authority over these decisions. All right, so any questions about how the governance of Compound works? Yep.
Is there any mechanism to avoid any one party by turning up with the supermajority of the government?
Yeah, that's a great question. So basically, comp tokens definitely cost money, and it would be very difficult for someone to have like that much money to buy out all the tokens. And at the same time, if someone were actually able to do that, then at that point, like there's other protocols that people can go to, and people might not trust Compound anymore if all the governance tokens are like held by a central authority.
But it would be possible.
Yeah, it could be possible, but like most people don't have like that much money to do that.
Maybe not person, but like the company.
Yeah. So like it could work. Theoretically, that could happen, but at that point, then like they would be king of like no one, because no one would trust the protocol as a whole if like one person or organization has that much control. Right. Any further questions about compound governance? Yep.
Like following up on that point, what's the relationship between the content you have and voting power? Is it like a compound to that is logarithmic or something?
So I'm actually not too sure about that, but I just know generally like the more comp tokens you have, the more voting power you have.
Yeah, I was just gonna like add to that, basically some DAOs decide that like the amount of tokens you have and the voting power you have is based on like a logarithmic scale. That just means that like as you approach infinity tokens, you actually get a diminishing return on the voting power that you're allowed to have. And so that mitigates the rest of like somebody being able to like buy up like 50% of the tokens and having too much power.
Yeah, thanks for helping to address that. Yeah, any last questions? All right, if not, we can just quickly summarize what we went over today. So some of the key takeaways about Compound from this lecture, basically Compound is a platform to let users borrow and lend crypto assets in a streamlined, decentralized fashion. So if you're a depositor, your assets get pooled together into a big like borrowing pool and can earn interest through C tokens. Borrowers, if you want to borrow out money from Compound, you have to over collateralize your loans and pay the interest. And your assets can be repaid as a borrower or withdrawn as a depositor anytime you want through the C token mechanism. The interest rates are algorithmically set based on the market forces, and Compound can be updated by a decentralized community with no real central control. And yeah, so that's pretty much it about Compound. Does anyone have any like last questions or just overall questions about how Compound works? Anything like that? All right. If not, thank you guys for listening.
Wait, start over. Hold on.
Oh.
Okay, now I'll go. Yeah, okay. Oh. Hey everyone. Oh wait, I don't have my mic. Where's the mic?
Oh, it's
Oh, here.
yeah, this thing.
Hello. Hey everyone, my name is Riddy and I'm in EQ Babby this semester. I'm a sophomore studying CS and I'm really excited to show you guys what zero knowledge proofs are all about. So, have you guys ever wanted to prove that you know a secret, but you can't really say what that secret is, right? So like, for example, let's say you're baking your famous cupcakes, but you don't want to reveal the ingredients. Or you're showing your friend like a magic trick, but you don't want to show them how you did it so that they can still be impressed by you. That's exactly what zero knowledge proofs allow you to do. And with this exciting new technology, you can prove that you know a secret without actually saying what that secret is. And that's why ZK-SNARKs, recursive ZK-SNARKs are so cool right now, because they're revolutionizing the way we think about privacy, security, and trust in the digital age. So if you guys want to teach your friends later about some cutting edge cryptography, make sure you tune into today's lecture. Please scan this because it has a bunch of definitions you guys may want to look at because it gets pretty complicated. And at the end, I like curated a bunch of resources for you guys from like beginner to advanced level for each topic. So yeah. If everyone scanned it, I will continue. You got it, Mo? Okay, so today we'll be going over background, zero knowledge proofs, ZK-SNARKs, recursion, recursive ZK-SNARKs, and Ethos. So this all sounds pretty intimidating, but it's okay because I'll be breaking it down simple by simple. Okay, so before I get into the nitty-gritty of things, I'm gonna be going over the history. So it all dates back to the 1980s, and in 1985, Goldwasser, Macaulay, and Rakoff introduced interactive proofs. And since then, it's been gaining a lot of popularity. And then the Golden Trio again in 1993 published their groundbreaking paper. And then after that, it's been gaining popularity. People are learning about it. And in 2016, a new cryptocurrency called Zcash became the first major application of zero knowledge proofs. And I'll be going over Zcash later in the lecture today. So before I begin with zero knowledge proofs, I'm going to explain cryptography for those who might not be familiar with it. So let's say you're in class and there might have been a time where you're passing notes to your friends because your teacher's boring and you don't want your teacher to know what they're saying. And I hope that's not happening right now, but that is an example of what cryptography can be. It's basically sending messages to one another without having interception, and you want this message to be secure. So it's the art of transforming information into a form that's unreadable, and no one's allowed to access it. So there's two different types of cryptography. There's symmetric key and public key. So let's say I want to mail a letter to Tiffany. I would use Tiffany's home address to send the letter to her, and to like open this letter would use her mailbox, which would be her private key. So I would send the letter to her home address, which would be her public key, and then her opening the mailbox would be her private key. So in the public key cryptography, you have public and private, but in symmetric, you have the same keys for both encryption and decryption. So in this picture, what's happening is that Alice wants to send a message to Bob, but she wants that message to be secret. So she's trying to say, Bob, stop trying to make fetch happen. I don't know, it's probably some like inside joke. And then she's gonna use Bob's public key to encrypt it into the string of letters and numbers. And then she's gonna, like Bob will use his own private key to decrypt to see what she said. So this brings us to zero knowledge proofs. So what are zero knowledge proofs? They're basically in cryptography a way to show that you know something without saying what that something was. So for example, let's say Alice wants to show Bob that she knows his birthday, but she won't say his exact date. She can use like a zero knowledge proof to demonstrate that she knows his birthday without saying the exact date. These are some fun memes. So why am I talking about zero knowledge proofs today, and why do they even matter? So they're very fundamental to modern cryptography, especially in applications using privacy, security, and trust. So logging into a website, like instead of putting your password into an unsafe website, you can use a zero knowledge proof to show that you know your password. Authenticating your identity, you know, when you have to download a whole dual mobile app and do all that stuff, like it's too much work. So you can just use a zero knowledge proof to authenticate your like identity. And one important one is sending private transactions. So in like Bitcoin, your transaction, like your ledger is public information, right? So if you want to send your information, like, so it's private, without like revealing your balances and all, you can use Zcash, which we will get into later. And there are super cool ongoing projects that we're going to be talking about Ethos at the end of the lecture. So does anyone have questions so far? Okay, so I'm going to be going over some fun examples. You guys probably might be familiar with Where's Waldo. So let's say Alice and Bob are trying to race to find where Waldo is in this picture. Alice says she knows where Waldo is, without showing his precise location. So the first thing she can do is she can cut off Waldo and then show it to Bob. Like, here, I found Waldo. And to make sure she just didn't take a random picture of Waldo, she can watermark the back of it. And then since she cut it out, the watermark will be behind Waldo. Another thing she can do is, instead of cutting Waldo out, she can cut out like the outline of Waldo, and then she'll place it over the picture, and it'll basically show, oh, I found Waldo, but it won't show where his exact coordinates are. So here's like a representation of that, just like going over it. So in order for a zero knowledge proof to be like complete and actual zero knowledge proof, it has to complete these three fulfillments. So soundness is one, and you have to prove that everything is true. Like, you can't cheat. Like in the first example, as I said, like Alice can't just show a random picture of Waldo. It has to be the same one that she showed, that is in that scene of people skiing. And the second thing is completeness. So everything has to be true, that she has to show that she actually found Waldo for it to be complete. And then zero knowledge. The only thing she can show is that her victory to Bob without anything else being publicized. So how does zero knowledge proof work? So I'm going to give you guys a general idea to keep in the back of your head. So what's going to happen is, like, the prover is going to do all this like math calculations that we'll get into soon. And the verifier will like verify these math calculations by doing the calculation. So I'm doing a bunch of these like equations and stuff, and then the verifier is like solving the equations. And zero knowledge proofs use a combination of encryption, hashing, and elliptical curving. And don't worry if that sounds very scary. I will get into that very soon. So here is an example of prover Alice and verifier Bob again. So verifier Bob is going to ask Alice to prove that she knows the secret data that hashes H. So this is a hash function. And in a hash function, you put an input and an output comes out. So what's verifier Bob is trying to make Alice prove is that what is this input that she has that makes this specific hash H. So she's gonna have to prove, using a zero knowledge proof, that she has this secret data that can make this specific hash H. Does anyone have any questions so far? Okay, so here are the types of zero knowledge proofs. So there's interactive, where the prover and verifier are exchanging messages, they're coming in contact with each other. There's non-interactive, where the proof generates without further interaction. So they might use like algorithms, different cryptographic techniques to exchange messages but not come in contact. And these types of zero knowledge proofs have different protocols, meaning like different methods to like complete the proof. So these are some examples here. Some might use like logarithms and polynomials. So I just covered a lot in this section. So as a summary, cryptography, a way to secure messages without interception. Zero knowledge proofs are an aspect in cryptography, and it's a way you can prove something without revealing its information. It's used in a wide range of applications as privacy, security, trust, and there's different types, and each come with like different protocols. Okay, questions again. Okay, now we'll get into the fun stuff. What are ZK-SNARKs? So ZK-SNARKs stand for succinct, non-interactive argument of knowledge. So these are a type of zero knowledge proofs that again will allow one party to prove they know something without revealing itself. So it just extends on the zero knowledge proof. So what makes it different from a regular proof, zero knowledge proof, is that it's non-interactivity and succinctness. So this is achieved with elliptical curve cryptography and pairing-based cryptography. So what's going to happen is that in this ZK-SNARK, you're not interacting with anyone, and it's what happens is that like the proof will happen like in a reasonable amount of time, a small amount of memory, and a small amount of computational steps. So this is what elliptical curve cryptography looks like. So this red line here is an elliptical curve. And it basically is a set of points that satisfy a mathematical equation. And usually that equation is in that form x cubed plus nx plus b. And it basically to generate the public and private key, you will use random points on the curve. So here, how it basically does its security is that So the line here, the curve, it's symmetric. That's one cool feature about it, is that it flips. It's like a mirror image. And then when you draw a line through this curve, it will hit no more than 3 points. And basically what the whole concept behind elliptical curve cryptography is that it's going to take 2 points and it's going to return 1. So here we see P and Q. And since we drew a line, P and Q will yield R. And you can do this all throughout the elliptical curve. So since it has a symmetrical feature, what it does is that from R, you can draw another, like flip it, and it will give you the symmetric R. And then to see which point like P and R will yield, you draw another line. So you just keep doing this throughout the elliptical curve, and you'll keep yielding, like 2 points yield 1 point. So you're basically taking 2 points and making 1 point. That's like the general idea of it. It's very complicated, and I can like make a whole lesson about this. So that's like the general idea you want to have. Does anyone have any questions about that or want to see the picture again? Okay, so we're going to use these cryptographies in Zcash. So Zcash is a cryptocurrency that was launched in 2016, and users can make their transactions private, which means that their transaction amount, their sender and recipient are hidden. And this is using ZK-SNARKs. So here are some fun memes again. How does it work? So at a very high level, what you want to think about is you want to turn this, what you want to prove, into a math equation, and knowing a solution to this equation basically. So quick example, let's say Alice says, I have 5 Bitcoin. She's going to turn this statement into a math statement. She's going to generate a proof to show she knows the answer to this math equation, and then Bob will verify doing his own calculations. So we're going to be going over how ZK-SNARKs are constructed in Zcash, and this kind of gets a little complicated. So if you guys have any questions, just raise your hand. So these are the steps. So first you go through computation, arithmetic circuit, R1CS, QAP, and ZK-SNARK. This all may sound complicated by now, but at the end of the example, you guys will know what it is. Okay, so first you want to turn your transaction validity function, which is a function when you're like sending transactions on like Bitcoin. This function, what it's going to be doing is seeing if your transaction is valid or not. So you want to turn this function into a mathematical representation, like an equation, like a polynomial. And how you do this is you break down the logical steps of this equation into the smallest possible operations, and you're creating an arithmetic circuit doing this. So this is what the arithmetic circuit would look like for computing this expression, a plus b times c. So the inputs here in this image are A and B, and A and B are going through gate 1, which is addition, and then B and C are going through gate 3, which is multiplication, and then they both will go through another gate, which multiplies them both. So basically what's happening in this arithmetic circuit, it's breaking down the equation into small components, putting the inputs in, they're passing through gates, and then you get the equation at the end, and you can think of these lines as like wires in the circuit. So then what happens next is that the verifier will use something called the rank 1 constraint system. And it's basically they're going to verify like these values, these inputs are traveling correctly across the line. So making sure like the inputs are going which gate it needs to go to. That's how it's verifying it. But for an example that like an arithmetic circuit could be very, very complicated. So instead of checking one by one, they'll use something called a QAP, and a QAP just turns these steps into polynomials. And basically, the verifier will use like this QAP to like bundle up all of these constraints, and then they'll take the 2 polynomials and match them at one chosen point. So to check if all the constraints work. And then while they're doing this, this is where the like ZK-SNARK part comes in handy. So this is what enhances like the entire like proof itself. So as we talked about in like elliptical curve cryptography, we use 2 points to generate 1 point, right? So let's say the prover knows like what the verifier is going to verify in advance. What's going to happen is that what if they just make the proof just to prove at 1 point and not all the points. So that's where elliptic curve cryptography comes in, where the 2 points yield to 1 point. So this keeps happening on the elliptic curve. So since this elliptic curve is checking all the points, like the prover can't manipulate it to her own way, if that makes sense. I'm just gonna keep this up here for you guys to digest it. Okay, so I just went through a lot of stuff. So here's a summary. So ZK-SNARKs, they have two key features. Then we talked about elliptic curve cryptography, which is based on mathematics of elliptic curves. There's pairing-based cryptography, which is based on mathematical structures called pairings. In the example, what I first did was we turned the function into a math equation. The math equation breaks down into an arithmetic circuit, and the verifier checks the constraints in the equation in the arithmetic circuit. QAD is a way to do this faster and build those equations together, and then ZK-SNARK enhances the proof. Does anyone have any questions or want to see anything again, like the pictures? Yes.
So what are you exactly approving?
Okay, so here in the Zcash example, what's happening is like the function, the transaction, where what we're doing here is proving that the transaction can be validated onto Zcash and basically you have to do all of this to make sure, like the ZK-SNARK part, make sure that the transaction is private.
Yeah, I'm referring to like the elliptical part. Like, are you proving that you have knowledge? Like, are you proving that you have enough points to find the elliptical curve itself?
Oh no, so what's happening is like, let's say like the elliptical curve part is just enhancing the entire like proof itself. So let's say the prover knows that the verifier is going to use this point, like this specific point. The prover can like manipulate the entire thing just to make sure that it works at this point. But in the elliptical curve cryptography, it takes the 2 points and it yields 1. So, and it's happening throughout the curve. So it doesn't happen like once, it happens multiple times. So this is ensuring that it works at all points, if that makes sense. So it's not ensuring like that there's points across the curve, it's just showing that in the proof that all the points work. Anyone else have any questions? Okay, so now that we're done with ZK-SNARKs, we're gonna go into recursive ZK-SNARKs. Before that, we'll go into what recursion is. So you can think of recursion as like a puzzle. You put it pieces and pieces together and it will show a whole picture at the end. So in this example of Russian nesting dolls, you're opening Russian nesting dolls until you get to the innermost, smallest Russian nesting doll. So you're basically opening it and opening it and opening it until you reach the smallest and most simplest level. So in programming, you're calling a function until it reaches its smallest, most simplest level, which is its base case. And in this case, the base case is the smallest Russian nesting doll. So in recursion, you're basically just repeating something until it reaches its like smallest, most final level. So that's like what recursive ZK-SNARKs uses. So it extends the capabilities of regular ZK-SNARKs, but it's just able to handle computations that involve recursive functions. So we're going to use the same example as before, but I'm going to break it down to how it works in a recursive ZK-SNARK. So as we saw, here's the arithmetic circuit again. And in a recursive ZK-SNARK, what we're going to be doing is taking each equation and we're going to be breaking it down. So here's the addition circuit and here's the multiplication circuit. So you're going to make it into sub-circuits. And that's where the recursion part comes in, where you're verifying each of these separately and not all together as we did in a ZK-SNARK. So for each of the sub-circuits, a ZK-SNARK proof is generated. And then the proof, so what's going to happen since the proof is generated for each, there's this like the big arithmetic circuit, and then you break it down. So then each sub-circuit is getting verified. And then after all of them are verified, I don't know if you guys heard of the Planck protocol. It's going to use it to make it into one entire single proof. So the point of this is like, why are we breaking it down? it just helps, the recursive structure just helps it go more fast. So like, instead of just proving the entire circuit, you're proving the circuits, like sub-circuits, recursively, so it's happening faster. So then the verifier will check that the values are traveling correctly along the wire, so meaning that the inputs are going where they need to. And then it's gonna get combined, and you're gonna use the QAP, so you're gonna like set the polynomial equations as we did in ZK-SNARKs. And so when the recursive ZK-SNARKs reaches its base case is when it will stop recursing. So in this case, like since output 2 satisfies the given constraint of the subcircuit, that's when the recursion will stop. Okay, so does anyone have any questions about that? It was similar to the first example, but what we're doing here is making the big arithmetic circuit into subcircuits. We're proving those, and then it'll combine into one. So the recursive structure is just helping it go faster, like the proof process go faster. So if anyone has any questions or want me to go back a few slides, let me know. So why recursive ZK-SNARKs? So as I said, they're very efficient. They allow for very fast and small verification of the computations. It makes privacy a lot better. There's a strong privacy. So since you're verifying each and every one of them, the privacy is there and security is there. And it allows for scalability. So it enables like efficient verification. So if it's so good, why isn't it used in everything? So why not recursive ZK-SNARKs is that it's very complex. Like implementing them could be very complex, and you really need to know like specialized knowledge. There's trust assumptions. So like if you like the setup phase, which is like the arithmetic circuit part, you really need to have it perform correctly or the whole proof just doesn't work out. And another thing is that it's computationally intensive and expensive, so it's not the most like environmentally friendly thing. Okay, so now we're going to be going over a really, really cool project using recursive ZK-SNARKs, and it won the hackathon in ETH New York. So last semester, so it's pretty brand new. So Ethos is a bunch of friends of Vitalik did this social experiment project using recursive ZK-SNARKs to demonstrate like the degree of separation between people. So like in mine and Tiffany's circle, how many people are in the mix of us, but we don't know who is in the mix of us. So we're trying to track who is in our circle without knowing who's in the circle. So you're keeping the individual friendships in between hidden. So in the steps of this, which we'll see in the video, is that users will receive the URL page, and then they'll the proof will use an NFT, and then you'll add a friend by signing authentication messages, and then you share the Ethos page directly to your friend. Then you sign the message, the circuit takes in the source node and the sync node, and then it'll connect the two, and then it'll basically create a cool graph, and then the ZK circuit generates a proof based on the path of the nodes. So this can be seen in the design of the project, which is right here. Okay, so this is their design. So it starts off by Vitalik adding his own friends to the circle, and then Bob continues to add his own friends. And then he adds his last friend. So now the last friend is on the graph, and he receives the proof. So here what's happening, so here what's happening is that the last friend knows he's friends with Vitalik, but he doesn't know how far he is away from Vitalik. So he knows from this graph, from this project, that he's 2 away, so that he knows that he's 3 degrees away. So the whole point of this project is to know how far you are from your friend without knowing who's in the middle. So that's where the ZK-SNARK part comes from. And then here's their user design, which is super, super cool. Okay. Okay, so the user starts by receiving the proof from their friend, and then they verify that proof. And then using the proof, they can either mint the NFT or just connect to their wallet. Well, they're connecting to their wallet and then minting the NFT. And then now they're adding their friend to the graph with their MetaMask wallet. So they're adding them with the name. And then they're signing the verification. And now the proof will generate. So then they're gonna press generate ZK proof. And now they'll take the address and then they'll send it back to their friend to show how far they are away from that friend. So this was just like a social fun project you can do with ZK-SNARKs. And yeah. Does anyone have any questions about the application? Okay, oh, sorry.
So that's actually pretty cool, but what would be the, like, why do we need this?
They just did it for their hackathon last semester. They actually won the hackathon, so that was pretty cool, but I think they were just doing it for like a fun, cool project just to show how ZK-SNARKs can be used in like many different ways. Yeah. But there's actually more like applications that are more useful than this. Okay, if anyone does not have any more questions, then that's the end of the presentation. I hope you guys had a fun time. Wait, hold on. I'm sorry. Why is it not full screen? Woo! I don't know why it's not full screen. Hold on, I'm gonna make it full screen. Give me 1 second. Ah, no.
Hi, hello, my name is Brent Friedman. I'm a second year EEC student and I'm an EduBabi. And today I'm going to be presenting Solana, talking about its speed, scalability, and some iffiness on its security. So first, just as an overview, we're going to go into what Solana is, the purpose of Solana, and the meat of this lecture is going to be on proof of history. And finally, we're going to talk about validation, scalability, and consistency, and talk a little bit about the blockchain trilemma. So what is Solana? So Solana is a high-speed L1 blockchain technology. So by L1, that means it's a layer 1 blockchain, meaning it's its own entire network, rather than an L2 like Polygon, which is like built on top of Ethereum. And so Solana implements smart contracts to host decentralized applications. These could be like DeFi applications or gaming applications or wallets or anything of that nature. And it attempts to solve the blockchain trilemma, which we've talked a little bit about in class already, but just to run over it, essentially there are 3 aspects of a blockchain that you want, which is security, decentralization, and scalability, but you can only have 2 of those. So let's say you want your blockchain to be secure and decentralized, then you'd be sacrificing the scalability of your blockchain. And the same goes for any 2 that you want. And so Solana says that, hey, maybe this blockchain trilemma doesn't actually exist. Maybe you can have a blockchain that's secure, scalable, and decentralized. So let's go a bit into the timeline and background for Solana. So Solana was created by Anatoly Yakovenko, and he was a Qualcomm software engineer. So he worked on distributed systems at Qualcomm. So he has a lot of knowledge on decentralized networks. And he's the current CEO of Solana Labs, which implements Solana and runs it. And Solana was first proposed in 2017. And as you can see by our timeline, Ethereum was launched in 2015. The Solana white paper came out in 2017. And then Solana was finally launched in 2020. All right, that was pretty chill. Is there any questions on that? All right, if not, let's move on. So let's talk about Solana and its purpose. So why do we need Solana? So Anatoly Yakovenko noticed that there were very slow speeds and high transaction fees on Ethereum. So as you can see, if you look at this image, Ethereum handles 30 transactions per second, and Bitcoin handles about 7. But Solana can handle up to 50,000 transactions per second, which is like mind-blowing. Like it's insane. And so how could he do this? He did this by proposing a new concept of proof of history, which introduces super high transactions per second and super low fees. So what is the issue that Solana solves? So in distributed systems, time agreement is a huge issue. So let's think about Google. Google has databases all across the world, and they all need to be in sync on time because some of this data might rely on time, like late fees or something like that, right? So each database center has its own atomic clock, which is managed by engineers. And essentially an atomic clock is like a clock that looks at the vibration of atoms to like make sure or to like measure time, right? So this time that they're relying on is they're trusting these engineers to maintain these clocks. So they're putting trust in certain entities to create a trusted source of time. But we don't want that on a blockchain. We need to be like totally decentralized, super trustless, so that we don't have to rely on anybody to create a clock, right? So other L1 blockchains lack in efficiency because of this time issue. So here's why timekeeping is an issue. So let's look at Bitcoin. So on Bitcoin, this comes from Bitcoin Wiki. A timestamp is accepted as valid if it is greater than the median timestamp of the previous 11 blocks and less than the network adjusted time of plus 2 hours. So as you can see, this is like a huge range of time where a block could be accepted as valid. And this is because of network latencies. So my clock on my computer is not the same as your clock on your computer, and timestamps can vary by upwards of an hour or so. And to prevent or to counter this, Bitcoin implements a block time algorithm which is set to 10 minutes. So this means that after, if you have 6 blocks, that's 60 minutes, where maybe 6 blocks ago, now we can validate that, okay, that block has been built upon, it is totally valid, and its timestamp is valid. And this can be exploited by miners because it would benefit miners to report an earlier timestamp, as the algorithm would then output an easier hashing target. So let's say if I just mined a block and I say, hey, I actually computed this block 5 minutes ago, and the Bitcoin network accepts this as valid, then the algorithm would give me a hashing target, which would only take 5 minutes to compute, when in reality, I just computed this block, so there actually should be the next block in 10 minutes. And so this is called the time warp attack, and it negatively impacts the crypto economy because there are more block rewards coming out at greater times, and this greater supply means there's lower value of the crypto. So Bitcoin has these rules in place, which are enforced by validators, and it ensures accuracy of time. These inaccuracies in time, which exist on Bitcoin and other networks, have huge implications for like late fees that depend, like I talked about earlier, like depend on time. So since blockchain technologies require a trusted source of time, how can we know if a miner actually submitted a block at the given timestamp and didn't say like, oh, I actually mined this block like 5 minutes ago? So Solana introduces a clever concept. We don't actually need to depend on wall clock time. We can just have an ordering of events. So if you look at this image, we can see that the circle comes before the oval, which comes before the triangle, or the square, etc., etc. All right, are there any questions? All right, if not, let's move on. Okay, so now here's the main stuff about Solana, the proof of history. So let's go into a little overview of the Solana network. So first we have our leader, which is the red kind of tilted diamond thing. And this leader is elected via proof of stake election of all the validator nodes just for this one proof of history sequence. So this leader takes in transactions from users of the Solana network and puts them in order and generates this final state. And then this leader sends this entire chain out to all the verifier nodes, which then recompute this final state and validate it by sending it back to the leader. So validators do all this work because they earn rewards like transaction fees. Though they may be small, they do earn rewards. Okay, so let's consider the one-wayness of SHA-256. If I put some input into SHA-256 and receive an output, that output is totally unique to that input. And any changes that you make to the input will be reflected in the output. So let's look at this sequence right here. So at index 1, we have SHA-256 of any random starting value, and then we get hash 1. We then put hash 1 into SHA-256 again to get hash 2. So the only way that you can generate hash 2 is by first generating hash 1. So let's run through a quick example. So if my input is literally the string any random starting value, then this is my hash, right? So I'm going to copy that hash. And then now what we're going to do is put SHA-256 onto that hash. So this top one is hash 1, and this bottom hash is hash 2. And so if you continue the sequence, you'll see that essentially we have a sequence of hashes which depend on each other. So the only way to get hash 3 is first by getting hash 2, which first you have to get hash 1, right? So it all depends on the first value that you have and then repeatedly applying SHA-256 to your sequence. Okay, so we can use an analogy to think about this. Let's talk about Hannah and Victor. So let's imagine Hannah is an honest note taker on great expectations and permanent marker, and Victor is a skeptical observer. If Hannah is like sitting at her desk taking notes on great expectations, and Victor walks over and sees that she's on chapter 3, Victor can conclude that Hannah has not only read chapter 3, but also chapter 1 and chapter 2. And this is because chapter 3 integrates context from chapter 1 and chapter 2 into the text that's in chapter 3. So if Hannah can understand and comprehend and take notes on chapter 3, she must have also read chapter 1 and chapter 2. So in this example, chapters would be our hashes in our sequence. So this is the essential equation for history. So the hash at index I is SHA-256 to the power of I, essentially like applying SHA-256 I number of times to our starting value. So because of the simplicity of the equation, this means that it's only necessary to publish hashes after a certain interval for verification. So if we're given this sequence where we're given the hash at hash index 1, 200, and 300, we can easily verify all 3 of these. So how would we do this? First, we can verify hash 200 by applying SHA-256 200 times to hash 1. Now, how do we verify hash 300? Well, we already know hash 200 is valid, right? So then we just apply SHA-256 100 more times to get hash 300. It's super easy, and it means that verification is extremely easy on the Solana network. So now let's think about how this sequence can reflect time. Since we know that the only way to compute hash 300 is by running SHA-256 300 times, we have proven that time has passed between index 1 and index 300. This is because applying this function SHA-256, though it may take like 1 millisecond, it still is time, right? Because of the uniqueness of SHA-256, you have to run SHA-256 300 times to go from hash 1 to hash 300. Okay, now let's bridge our intuition from timestamps to hashes. And let's assign each account to each hash. So if you're looking at this sequence right here, you can see that hash 3D039 has account 5101458555 blah blah blah, right? Then down here, you see this one has account 51014669. So this one is some magnitude of 10 further down the chain than that above hash. And we can compute this hash by running SHA-256 some amount of times to get that bottom. So we can use this count of how many times we've applied SHA-256 as a timestamp, essentially. Okay, so what's the point? Like, yeah, we have like these SHA-256 sequences, right? Like, okay, we can like keep track of time, but like, how can we utilize this concept in an innovative way to revolutionize the blockchain industry? Yakovenko thought that we could use this for timestamps for events. So let's use hashes to timestamp data. Let's think about a naive approach. Let's say a photographer takes a picture and writes the current hash on the running sequence on that Polaroid printout. Can we trust that that photographer actually wrote down the hash at that exact time? What if the photographer is dishonest? How can we prove that that photo was taken at that certain hash? Solana thinks about this situation in a totally revolutionary way and introduces a genius alternative. What if we actually integrated that photograph into the sequence? Rather than writing the current hash on the Polaroid, what if we took that Polaroid and threw it into our hash machine, and now it's integrated into our sequence? So let's look at this example here. We have our current hash sequence that we've already looked at before, right? From hash 1, hash 200, to hash 300. Now, let's say at hash 336, our photographer takes this picture, right? Instead of just writing hash 336 on the picture, we're actually going to take the SHA-256 of the data of that image and append it to hash 335. Then we take the SHA-256 of that entire data to compute hash 336. So again, I want to iterate the uniqueness of SHA-256 and the one-wayness. The only way we can get hash 336 is now if we have the data from the photograph that was taken. Otherwise, there's no way of computing hash 336. Now let's just extend it a bit. Let's look at the same sequence, but added on a few more indices. So we have hash 1, hash 200, hash 300, hash 336 with our image that we just computed. And then let's continue our SHA-256 sequence going to hash 400 and hash 500. And then let's say at hash 600, another photographer takes an image and he appends it to that last hash that he saw, hash 599. And then now it's implemented in our sequence as hash 600. So here we've proven that photograph 1 comes before photograph 2. And we've done this in an integrative way, meaning that the data is integrated into our sequence. And the only way to get hash 700 is by appending the hash of photograph 1 before the hash of photograph 2 in our sequence. Okay, cool. Like, yeah, we talked about like photographs and stuff. Like, that'd be nice to know like when a photograph came before another, right? But we can actually extend this, and we can use this knowledge to input any data that we want into our sequence, meaning like transactions. So every node observing the proof of history sequence knows the ordering of our SHA-256 of our hashes. So here, a change in the sequence is denoted by coloring. So we have a blue sequence where the index is like 5101, 144, blah, blah, blah. But then at the next one, we input data, And now the entire sequence has changed because of the uniqueness of SHA-256. Okay, now let's go back to our analogy. Let's talk about proof of history with data, and let's talk about Hannah and Victor again. Let's say that Hannah is such a good student that in her notes, she actually copies images from the book, right? So let's say that if Victor comes over and sees that Hannah has an image at chapter 2 and Hannah has an image at chapter 3 in her notes, Victor can then say for sure that the image at chapter 2 actually is shown in the book at chapter 2 before the image at chapter 3 in the book, right? So essentially, Hannah has a sequence of time where she can say that this image comes before another. All right, so that was quite a bit, so I'm going to stop and ask, are there any questions? Yep.
So in the beginning, when you were talking about the structure with a group leader, I was like beginning to like you start off with proof of stake and you get a group leader. Like
right here.
how is that decentralized? Like you just have like insane amount of verifiers, but like from my understanding, this is not decentralized.
So essentially what's happening is there's a pool of validators, right? There's a pool of nodes working in this network, right? And so every time that we want to generate a new proof of history, right, or a new block, essentially, we're going to hold an election based on proof of stake. And so this election is totally decentralized. It's based on a consensus mechanism, which I'm not like going to go into really, but is decentralized in nature, where any validator has the opportunity to become the leader for that proof of history sequence. Does that make sense? Okay. Are there any other questions? All right, if not, we'll move on to verification. So on Solana, you can perform validation in parallel. So on a GPU, you can split up the final proof of history sequence into portions that can be handled by each core. So let's say we have our hashing sequence, which goes from index 200 to 300 and from 300 to 400. Instead of using just a single core to run SHA-256 200 times from index 200 to 400, what if we split it up and had one core do 100 SHA-256s and another core do another 100 SHA-256s? So let's take index 200 and put it at core 1, and we take index 300 and put it at core 2. Now, if core 1 runs SHA-256 100 times and comes up with index 300, and core 2 runs SHA-256 100 times and gets hash 400, then if hash 300 matches the hash 300 in core 2, we can say that from index 200 to 400, we are totally valid. So essentially, you're splitting up this 200 SHA-256s up into 100 SHA-256s for 2 cores. And so since GPUs can have up to 4,000 cores, you can imagine just how much we can actually divide this sequence up. So as a result, validation is far quicker than generation. This is because generating this SHA-256 sequence, it has to be done on one core. Since we don't know what like certain hashes are at certain indices already, we have to generate it on one core. So let's take a look at some equations. So the expected time to produce a sequence is the total number of hashes that we have over the hashes per second for one core. Well, the expected time to verify is the total number of hashes in our sequence over the hashes per second per core times the number of cores we're able to verify. So using these equations, let's say we have 100,000 hashes in our proof of history sequence, and we have 10,000 hashes per second per core. In reality, this is much higher because miners can compute up to 89 quintillion hashes per second. And let's say we have 4,000 available cores. So to generate our proof of history sequence, it would take 100,000 hashes in our proof of history sequence over 10,000 hashes per second for our one core. So that would take 10 seconds. But to validate this proof of history sequence, which was generated in 10 seconds, we have 100,000 hashes in our proof of history sequence over 10,000 hashes per second per core times 4,000 available cores. So to validate this sequence, it would take 0.0025 seconds, which is absurdly fast. So here's an image of cores computing in parallel. So each core computes a slice of the proof of history sequence and checks if the inputs and outputs match. So if we have, let's say, index 100 to 200 on core 1, and then from 200 to 300 on core 2, they would both run simultaneously SHA-256. And if the input to this one matches the output of that one, then we're good. We can say it's valid. Are there any questions? All right, if not, let's move on to scalability and consistency. So what is scalability in blockchain? So in blockchain, we have vertical and horizontal scaling. So horizontal scaling would be like adding more nodes to the network. And vertical scaling would be making our nodes more powerful or capable of handling more computations. So the whole goal with scaling is to optimize throughput of the network. So let's talk a little bit about horizontal scaling. So let's talk about sharding. So this is where you would split data or workload up against multiple entities. So here, if we have a collection of 1 terabyte of data, if we sharded this data, we would have 4 shards, each having 256 gigabytes of data. But when we split up this network, now it's hard for us to make sure that each shard is working honestly. And so in a decentralized network, it introduces complex consensus algorithms to make sure that each shard is working in the correct direction and acting honestly. So then that begs the question, is it possible to scale horizontally without sharding the network? We'll see that we can in Solana. So we can split the workload of each leader amongst multiple leaders. So let's say we have 2 leaders, each generating their proof of history sequence. Let's say that at hash 2 for generator B, we take hash 1A and use that as data to generate hash 3B. Now we can say that hash 3B came after hash 1A, which is in some other leader's generator, right? So now we can say that hash 3B in time comes after data which is not even on our proof of history sequence. Similarly, if we append hash 1B to hash 2A and generate hash 3A, we can now say that hash 3 came before hash 1B in some other sequence. So now this is also transitive, meaning if we have A synchronizing with B and B synchronizing with C, we can determine ordering of events between A and C, not just between A and B and C. So this implements more horizontal scaling, because instead of overloading one generator with lots of transactions, we can simply divide that up amongst multiple leaders who each implement this transaction data in their own proof of history sequence and synchronize at certain intervals. Okay, like I just said, so periodic synchronizations allow for traffic to be split up. And so this allows for traffic handling at a cost of some exact time accuracy due to network latencies. So if, for example, we have this the example that we had from before, we can't say like, oh, hash 3B comes exactly 2 hashes after hash 1A. We can simply just say hash 3B comes after hash 1A. So it's not super accurate about where exactly the hashes come, but we do have an ordering between the two. Okay, now let's go back to our analogy. Let's talk now about Hannah, Harry, and Victor. So let's introduce Harry as an honest note taker on Oliver Twist in permanent marker. If Hannah's going along her way, taking notes on Great Expectations, and then in chapter 2, looks over at Harry and notices that Harry is on chapter 1. Let's say she writes that in her notebook on chapter 2 and continues reading and taking notes on chapter 3. Now, if Victor walks over and looks at Hannah's notebook, he can conclude that when Hannah was taking notes on chapter 2, Harry was taking notes on chapter 1. So essentially, Victor can gain information on Harry or a timeline on information on Harry without even looking at his notebook. he just looked at Hannah and saw that Hannah said that Harry was taking notes on chapter 1. And this is because Hannah is honest. Okay, so let's talk a little bit about consistency. So what if a malicious generator listed events in reverse order? So this would mean that the generator had access to these events before the sequence generation. So here, let's say that the generator has event 1, 2, and 3 listed in the correct order in sequence A, but behind the scenes, they're also making another sequence B where they listed them in reverse order. Event 3, event 2, and event 1. This would have huge implications, obviously. If you're dealing with transactions, the timing of these transactions matter immensely. So we combat this by having each event implement the last hash seed. So an event also, just to clarify, could be a transaction or whatever, some sort of data that we want to implement in our sequence. So back to what I was saying, each event should implement the last hash seed. So if we have here that event 3 appends hash 30A to its event, then it's impossible for the attacker to place this event before hash 30A. Because again, the uniqueness of SHA-256 means that you need hash 30A to generate hash 40A through our event 3. And so this process requires private key verification so that the generator cannot alter this last hash scheme. So otherwise, the generator could just go in and append hash like 50A or 60A and push down that event. But since we're requiring our private key verification, the generator doesn't have access to do that. Okay, let's look at consistency a little continued. So here we have our blue sequence at hash 0x dead beef. And then at this hash here, we're going to implement some data, some event data, and we're going to say that the last hash we saw was 0x dead beef. And then we have the hash of our event, and we put that into our new sequence. So now, because this data relies on the last hash scheme, 0x dead beef, the generator cannot put this data anywhere before 0x dead beef. Okay, so that was a little bit. So are there any questions? Okay, if not, I'm going to move on. So let's continue with the blockchain trilemma. So let's recall the blockchain trilemma, which we talked a bit about earlier in this lecture. You have scalability, security, and decentralization, and you can only choose 2 in a blockchain network. So let's talk a little bit about efficiency. So utilizing the parallel processing, which I talked about earlier, and the horizontal scaling, Solana has been able to gain theoretical speeds of over 70,000 transactions per second, which is like more than Visa, more than any other competitor. This slide says 50,000, but it has since been updated and they have theoretical speeds of 70,000. And so this universal source of time reduces the validation process on the network. So then this begs the question, is Solana better than Ethereum? Because if you look at this graph, you can see that Solana has 65,000 or 70,000 transactions per second, while Ethereum can only do 15. And the average fee per transaction on Solana is a fraction of a cent. And on Ethereum, it's $15. But one thing I'd like to note is if you look at the number of validators on Solana, there's 702. While on Ethereum, there's 11,000 plus. So let's also talk a little bit about the Solana ecosystem. These are just some projects that are hosted on Solana. We have Serum. This is like a DEX. Ledger is a wallet. So you can see there's a lot of applications that are hosted on Ethereum or on Solana. And so, like I noted in the 2 previous slides, since this network is relied on such high-powered GPUs, which are very expensive, it leads to a small number of validators. So the previous 2 slides before may have not been accurate, but there's currently 1,698 validators, which is compared to 10,000 on Bitcoin and 500,000 on Ethereum. So this begs the question of is Solana really that decentralized? So let's look through our cost of participation in the network. These are the requirements if anybody knows anything about computers, just very powerful computers. Essentially one GPU costs $12,000. And the number of cores is 96, which is pretty absurd. So let's talk a little bit about Solana Labs. So there's some controversy surrounding Solana Labs because as you can see here, in their initial token allocation, they allocated 50% of the tokens to themselves, which is kind of suspicious. And if you look at Ethereum, they allocated only 15% to themselves. So essentially Solana Labs owns a lot of Solana. Also, there's a lot of controversy surrounding outages on the network. And so obviously when you have outages on a decentralized network, that begs the question of how decentralized it really is. And Solana's reputation is not that great because they own so much of the network. And this is why the price has gone down so much in the past 2 years. So you can see it was $260 in 2021, and now it's $24. Also, Solana Labs was very involved with FTX, and after its downfall, obviously it's not a good look for Solana. Okay, are there any questions? All right, if not, that's it. Thank you guys for listening.
Let's give a final round of applause to Brent, Riddy, and William. Here's your attendance code. It's Babbies or babies. And capitalize the first B.